Okay, so we can start. Last time we considered problem number 2. Yeah? And we still have problems number 3 and 4 to consider. And someone was asking me whether I could tell what to do with problem 3. So one student had a difficulty with problem number 3. What's this one? What's this one? Good. So problem number 3. We have differential equation with parameter. And the question is, what condition should satisfy function g so that at 0, 0 we have transcritical bifurcation. So at 0, 0 transcritical bifurcation. So what conditions should satisfy this function? Any idea? We can start with definition of transcritical bifurcation, or definition of any bifurcations we know. So let's consider, okay, I will keep this y dot equals to some function f of y and c. Then let's take Taylor expansion, let's say second order Taylor expansion at 0, 0. Then f of y c will be equal to f at 0, 0 plus derivative of f over y at 0, 0 times y plus derivative of f with respect to c at 0, 0 times c and 3 second order terms here. Second derivative over y times y squared plus mixed derivative at 0, 0 y times c, and last term is second derivative, half of second derivative over c at 0, 0 times c squared. There will be more terms, but it's already cubic terms at the time. Who remembers what condition should satisfy this function to have bifurcation at 0, 0? Bifurcation point at 0, 0, what does it mean? Bifurcation point means that we have an equilibrium there, fixed point, and this fixed point should be non-hyperbolic. From the fact that 0, 0 is fixed point, we conclude that what? If 0, 0 is fixed point, let's put it like this. If y star, c star is fixed point, then what? Any idea? Then our function at this point should be 0, because it's fixed point. At fixed point, nothing is changing. Nothing is changing means derivative is 0. Derivative 0 means f is 0. Yeah? Good? So this means that f at y star c star is 0. But in our case, we are talking about y star c star is 0, 0. So therefore this is 0. So it is conditioned for 0, 0 to be fixed point. And if this point, fixed point, is non-hyperbolic, what does it mean? Next question. What means, this is not a very good term, but what should be extra condition for function to have bifurcation point? Remembers? Derivative, yeah? So this derivative should be 0. I can try to explain it. I can try to explain it. So assume at 0, 0 we have fixed point, and assume that this derivative is non-zero. Yeah? Then if this derivative is non-zero, this doesn't matter if it is 0 or not, I think. Okay, assume this is also not 0. So this is non-zero. We will keep this one, because it could be 0, could be not. And we neglect all second order terms. Yeah, we can do it. Therefore, we will have y dot equals to derivative of f over y at 0, 0 times y plus derivative of f over c at 0, 0 times c. So what we see that if y is 0 and c is 0, y dot is 0. Fine, yeah, fixed point. If otherwise, what would be fixed point if c is non-zero? If c is non-zero, then our fixed point will be, so it should, all of this should be equal to 0. Then y will be equal to minus derivative of f over c at 0, 0 times c divided by derivative of f over y at 0, 0. So we can do it because we assume that this is non-zero. Yeah? So we can do it. And what it means? It means that if our parameter is, if it was 0, 0, 0 is fixed point. If c is non-zero, then fixed point is changing. So fixed point will be c, and this y. This will be our fixed point, correct? For any c we find y, and with this y dot will be 0, and therefore it's fixed point. And if we will check, so the stability depends on this derivative, and if this function is smooth, then slight change of y and c should not change its sign. Agreed? If it's continuous. Therefore, sign of it doesn't change. It slightly moves. Therefore, what we see that if we change c a little bit, our fixed point slightly changes, but its stability is not changing. So nothing happens. There is no bifurcation. Yeah? So if we know that if number of fixed points is not changing and their stability is not changing, we don't have bifurcation. And this is exactly, as soon as this is non-zero, we will have no bifurcation. The question is, when this is 0, we will have bifurcation or not. It is, well, it is not, the answer is not unique. But if this is non-zero, then we definitely don't have bifurcation. Good? Okay, then what we do, since we assume that at 0, 0 we have bifurcation, we conclude that this guy should be also 0. Fine. And Next question is what kind of, so if this is 0 and this is 0, most likely we have bifurcation. What kind of bifurcation we have depends on further terms. If this non-zero, well, I will put it like this. Who remembers what are conditions for fold bifurcation? Fold, well, you just remember that fold bifurcation is something like this. Y dot equals to y, let's say, plus y squared plus c, something like this. Then you can see straight away that depending on c, you will have two fixed points, or none. Yeah, you see it? Just remember this. And this means that this guy should be non-zero. These guys. And this goes over there. Yeah? You recognize it. So this, if these two terms non-zero, we will have fold bifurcation. So this is, it's called non-degeneracy condition of fold bifurcation. But if you remember something like this, it is easy to remember. Normal form is slightly different. Normal form would say plus minus plus minus. So it doesn't matter whether there are pluses or minuses, you will have fold bifurcation. One out of four possible modifications of fold bifurcation. Agreed? Did you watch this lecture? You remember lecture? Yes, so it was basically about this. So, and then but we want to have transcritical bifurcation. If we want to have transcritical bifurcation, then this guy should be 0. If we want to have transcritical bifurcation, do you remember who should not be 0? Who remembers this? How should look like simple way, simple function, which gives you transcritical bifurcation at 0, 0. Anyone? For example, you see here, if we say this is 0, from this follows that either y is 0 or y equals to minus c. We have two roots always. I mean, when c is 0, they coincide, but otherwise we have always two roots. Why we have here bifurcation? No, we have here bifurcation because when c changes its sign, when c is 0, this and this coincide, but when c changes its sign, there are stability swapping. You can check it. So this is why it's called transcritical bifurcation. And now we can see that this guy is indeed this term, but this guy should come here. See here we have less, here we have less. Therefore, for transcritical bifurcation, this should disappear, it is 0, but these two guys should stay. These two guys should not be 0. Okay, and then we can come back to, so what we know, I will put it like this. This is non-zero, and this is non-zero. What we want to do now, we want to get back to this. So I was talking about this function f, but in fact what we have is this. Yeah? Okay. So what we have is f equals to, like this, f of yc equals to y times g of yc. This is what we have. Now, if f at 0, 0 equals to 0, so f at 0, 0 will be equal to 0 times g of yc, and this is 0. It's fine. Satisfied. Doesn't matter what is g, we have this. Correct? Next condition is this. Derivative of f over y at 0, 0 will be equal to derivative of this over y. Derivative of this over y, we use product rule, yeah? It will be g at 0, 0, derivative of y equals to 1, plus y times derivative of g over y at 0, 0. And we know that this guy should be equal to 0. It should be equal to 0. This y at 0 is 0, so it's 0 times this. And from here we conclude what? We conclude, in order for f derivative of f over y to be 0, this g at 0, 0 should be 0. This is first conclusion. First conclusion is g at 0, 0 should be 0. It is our first conclusion. Now, this should be 0. Yeah, this should be 0. Correct? We decided it. So let's find out what is this. Derivative of f over c at 0, 0 will be equal to derivative of this guy over c, which is y times derivative of g, but y is 0 at 0, so it's derivative of g over c at yc, and this will be equal to 0 because y is 0. No extra condition. Now this second derivative over y should not be 0. Second derivative over y of f will be equal to second derivative of this guy over y. So this was first derivative, then second derivative will be derivative of g over y at 0, 0. It's derivative of this over y, and here will be y times second derivative of g over y. This is 0, you remember, and plus derivative of g over y at 0, 0. Yeah? Agreed? And then what we know that this should not be 0. Therefore, this should not be 0. So this term is 0, disappears. This and this are the same, so this guy should not be 0. So therefore, second condition is derivative of g over y at 0, 0 should not be equal to 0. Okay, and second, so this we have derivative of f over c, and we should take derivative of this over y, yeah? Or we could put it as way around. This is derivative over y, and we should take derivative over c. Second derivative of f over c will be equal to, okay, we can take, so here it is y times derivative of g over c, it should be mixed derivative, sorry, and we should take this derivative over y. Yeah? Is it correct? Agreed? This will be equal to y times mixed derivative plus this derivative of g over c at 0, 0. Here should be at 0, 0. And this is 0 because y should be 0. And all of this should not be equal to 0. From where we conclude, last conclusion is, what conclusion is here? This should not be 0. This equals to this plus this. First term is 0, therefore second term should not be 0. Yeah? So this is 3 conditions we got. If we have this flow, this differential equation, and function g satisfies these 3 conditions, g at 0, 0 is 0. Derivative of g over c at 0, 0 is non-zero. The derivative of g over y at 0, 0 is also non-zero. Then at 0, 0 we will have transcritical bifurcation. Questions? I think, so this, I took it, something like this was in lecture notes also. I don't remember if I recorded this in my video lectures. Just a minute. Yeah, it is on page 12. On page 12, I consider this, I call it important example, and it's basically what we talk about here. You can double check it again. So I remember I set it as homework problem some time ago, long time ago, because I saw that it's good if students will just reproduce all these derivations. But eventually, well, now it is, that time it was free, so homeworks were for fun. They were not marked. And problem number 4. Problem number 4 generally is a theory. We can talk again. Do you have any questions here? I will remove. Problem number 4. So again we have differential equation. And the question is, what condition should function f satisfy to have pitchfork bifurcation at 0, 0. So 0, 0 pitchfork. And what condition should this function satisfy to have? Most of this was answered in previous example, generally, yeah? So it's again, so it's same problems. So if at 0, 0 we have pitchfork bifurcation, therefore at 0, 0 it should be equilibrium. It should be non-hyperbolic equilibrium. Then it should be, so there should be a degenerative condition for fold bifurcations satisfied, and then degenerative condition for pitchfork condition satisfied, and then eventually, if everything is like this, and then extra condition what should be non-zero exactly for pitchfork, then we will have pitchfork. Yeah. So it is again the same. Now the only difference is that fold bifurcation and transcritical bifurcation, they can be derived using second order approximation of function, while for pitchfork we need to use third order approximation. Again, f of yc, so we use, it's called Maclaurin, yeah, Maclaurin series. Do you remember what is the difference between Taylor and Maclaurin? Who remembers?
It's Maclaurin at 0, 0.
Yeah. So what I was doing, in fact, it was Maclaurin. Well, it is sub-case of Taylor series. So, okay, I will call here Maclaurin, yeah? This Maclaurin series is f at 0, 0 plus derivative of f over y at 0, 0 times y plus first derivative over c at 0, 0 times c. Then we have second order terms. Times y squared, mixed derivative. Second derivative over c. And we will need also cubic terms. I don't remember what it was. Plus 1 over 6. Third derivative over y. 0 to 0 times y cube plus, so it should be half, yeah, as far as I remember. Y squared c plus half ycc at 0, 0 times yc squared. Last term is 1/6 third derivative over c at 0, 0 times c cube. Okay? It is cubic approximation. There should be more terms, but we will not consider them. Let's stop at third order approximation. Now, all as it was before. So we want at 0, 0 to have pitchfork bifurcation, therefore it should be equilibrium point, and this should be non-hyperbolic equilibrium point. These two conditions should be satisfied straight away, because it is bifurcation point. Then, if we want for it to be pitchfork, then we can conclude that it's not fold bifurcation. If it's not fold bifurcation, this should be 0. Then, if this is not transcritical bifurcation, this should be 0. And this is all what we need. then everything. So and then what extra conditions like this is not 0 and this is not 0. So these terms are important for pitchfork. Do you remember? So again, maybe I will show you. Just remember how pitchfork looks like. Y dot equals to yc plus yq. Something like this. We can put here plus minus to make it normal form, but it's generally independent of this signs. It is how it looks like. The idea here is that here we have how many equilibrium points we have here? Question. From 1 to 3. Either 1 or 3. Yeah? So 0 exists always, but two others, like c plus y squared equal to 0, means that y two other roots are plus minus square root of minus c. If c is negative, they exist. If c is positive, they don't exist. Yeah. So we have either 1 or 3. This is pitchfork bifurcation. Pitchfork bifurcations again. There are 4 forms of this. 2 forms called subcritical. 2 other forms called supercritical. I can illustrate it here. So this is, let's say this is 0, it tends to be unstable. So this is so here, let's put it like this. Y dot equals to what? Can you tell me what I should put here? Oh, I will put it like this. Yc and yq. What signs I should put here to get this?
Minus.
Minus where? Here.
No.
Here.
Yeah.
And here plus. If c is positive, it is unstable. 0 is unstable. If c is negative, it's stable. And then, if for positive c, we have to, yeah, it is correct. Good. So this is what it means. 0 is stable, so this is c, this is y. When c is negative, 0 is stable. When c is positive, 0 is unstable. Then, when c is positive, we have 2 extra equilibria, and they should be stable. This is called supercritical. Supercritical pitchfork. There is another supercritical pitchfork. I will plot it here. How, any idea how looks another? So here it will be unstable, so it again c, y. 0 is unstable for negative c, stable for positive, and 2 other roots appear for negative c, and they are stable. It's also supercritical. And subcriticals should be like this. This in subcritical, this is unstable. But if this is unstable, this should be stable, and this should be unstable. This will be subcritical pitchfork. And here it's the same. To make it subcritical, this should be unstable here, this should be unstable, this should be unstable, and this will be stable. So there are four versions. And now it's subcritical. Yeah? Okay, and this is, it depends on these signs. There are 4 different ways to put signs, and for each of these ways we have one of these bifurcation diagrams. So in 2 cases we will have supercritical. Supercritical would mean that these two extra roots, they are 2 extra equilibria, they are stable. If they are stable, then supercritical. If they are unstable, subcritical. Okay, and now maybe I will tell you why. Why only this is enough. So what we decided? We decided that these 3 guys are zeros. Okay, well, I will remove them. Then this should be also 0. I will put it like this since all of them disappeared. I will have it here. Yeah. Everything else was 0. So what is important? This should be non-zero and this should be non-zero. Why others are not important? Question. Assume, so what the question, I will put it a different way. Why we need cubic terms? Assume we have y dot equal to, let's say this one, whatever it will be, yc plus c squared. Then here we have a problem. What kind of problem we have here? So what we did, we ignored everything except for first and second order terms. And by ignoring, say, third order terms, we got into trouble. If c equals to 0, then how many equilibrium points we have? Infinitely many. Any y would be equilibrium point. Because if c is 0, this 0, this 0, doesn't matter what is y, we will have, so y will not change, y dot is 0. Yeah? Do you understand it? So equilibrium is when y is not changing. Y is not changing means y dot is 0. And y dot is 0. If c is 0, it will be 0 plus 0. Y dot will be 0 independently on y. Therefore, any y would be equilibrium. And on the other hand, if c is non-zero, then we don't have at all any equilibrium. Then independently on y dot will be non-zero. You see, so this is a big problem. So it is kind of singularity. Therefore, to avoid this, we add these other terms. I will ignore all these derivatives, I will just use once. Yeah, it will be y cubed plus y squared c plus yc squared plus c. Let's put it like this. These factors are not very important for now. Assume they are all non-zero. If some of them are 0, doesn't change anything. Now, since we added these terms, cubic terms, at least one of them should be of the same order as at least one of second order term. Yeah. So something here should be not smaller than one of these two terms. Agreed? Now, you see, we have here c squared and here c cube. If c is very small, then c cube is much smaller than c squared. Agreed? We will put it like this. So generally when we do this, so the question now that we have this formula, is there a way such that we can ignore some terms here? What we found out that cubic terms we need. Without cubic terms, at least we need at least one cubic term, but we don't know which one. For now we have all of them. So what the question here is that c tends to 0, y tends to 0, and if these two guys tends to 0, then what is then what terms are considerably smaller than others? Which terms we can ignore? Then, for example, c cube is much smaller than c squared. Agreed? Therefore, this can be removed. Then yc squared is much smaller than yc, by the way. Agreed? Because we multiplied this by something very small. Therefore, this also. And we can say the same. Y squared c is much smaller. Well, whatever. We can, for example, yc also. Agreed? So this is what's. And now this somehow should stay. Otherwise, if this disappears, then we will get back to our problem with quadratic approximation. Under what conditions this y cube could be of order of any of these two? The answer is like this. Yc, for example, should be of the same order as y cube. This is doable, provided that y squared is of order of c. You see, if we c tends to 0, y tends to 0, but if c of order of y squared, then we replace c here by y squared and we'll have y cube. Good? So what we got? We got that y squared is of order of c. If y squared is of order of c, then yc is of order of c cube. No, other way around. If we are, I will put it like this. So from here we conclude that y to the power of 4 of order of c squared. You see? And this guy is c squared. This guy is much smaller than this guy. Eventually. So we can ignore this also eventually. And what we got is exactly what was there, yc plus y cube. And well, basically I already put it, these conditions. So these conditions, it is not like you should derive something. You just listen or read lecture notes or listen video lectures and just try to reproduce, just writing down what you heard or what you read is good enough, so you will remember it longer. At least you will bring it. Because I don't put this kind of questions in the exam paper. The exam paper is something to derive. For exam paper, we will have time. We'll have like 6 minutes. For exam paper, you can practice with exercises in lecture notes. On page 19, there are 4 exercises, and some of them have 3 sub-exercises. We will consider one of them. If you have them, you can just ask me which one to look at. Okay, I will start with one. We can do more on Monday. Anyway, Monday we still will stay in this topic. So, 1a. So we have this flow x dot equals to 1 plus rx plus x squared. And we're supposed to find, so x, any x, in fact, r is also a real number. And we're supposed to find bifurcations which take place, find bifurcations. So formal way, if you're not sure what to do, just strictly follow formal way. Formal way says the bifurcation point is a point where we have non-hyperbolic equilibrium. Non-hyperbolic equilibrium means 1 plus rx plus x squared equals to 0, and derivative of this also 0, r plus 2x equals to 0. So solution of this is bifurcation point. So here r, from here we conclude that r equals to minus 2x. We put it there, and we get 1 minus 2x squared plus x squared equals to 0, which means that 1 equals to x squared, which means that x equals to plus minus 1. So, and for each of them, if x is, r is minus 2x, therefore first fixed point is like minus 2, 1 minus 2. It is first, and second will be minus 1, 2. So we have two bifurcation points eventually. Yeah? What kind of bifurcations are? Can you say, looking at what is in here?
Maybe fold.
Fold, yeah. Because looking here, we see that there will be either two roots or none. Yeah. Yeah, okay. So what? Again, formally, you can make to understand this. Again, formal way, long way, is to take Taylor expansion at this point. F of 1 plus rx plus x squared will be equal to 1 plus, let's say we take around this point, plus 1 times minus 2 plus minus 2 squared. This is f at 1 minus 2. Yeah? The next will be derivative of this over x, which is r plus 2x. R plus 2x. Well, I will put it like this. It will be confusing. This will be confusing. I will do it different way. So we will put it like this. F of x r equals to f at 1 minus 2 plus derivative of f over x at 1 minus 2 times x minus 1. You see, yeah? Plus derivative of f over c at 1 minus 2 times r x minus 1, r plus 2. Do you understand what I'm doing? Yeah? Is it okay? This is our function. This is our first bifurcation point, and around this bifurcation point we make Taylor expansion. So next should be second order terms. That 1 minus 2 times x minus 1 squared, and so on. There are two extra terms. You can just calculate them and put them. As I said, it is formal way and it is log way. Easier way may be to look straight up there. 1 plus rx plus x squared equals to 0. And here we find that x 1, 2 equals to minus r plus minus square root of r squared minus 4 divided by 2, yeah? And then we can see that they exist when r squared more than 4, which means that r, if r, let's say, perhaps it will be more than 2, r is less than minus 2, or r is more than 2. So minus 2 and 2 will be our bifurcations. And we see in both cases there appear two roots. The only way to conclude it is to find out which root is stable, which one is not. Usually, okay, last story. Usually I ask to plot bifurcation diagram. I used to ask at least. So one point is x equals to 1, r is minus 2. So it is this point. And second point is x is minus 1 and r is 2. This point. So it's here and here we have bifurcations. So this, it is here when r is, and it is here. The only point is to find out, so we have here two roots, which one is stable, which one is not. Derivative is r plus 2x. So x should be, if x is large, it will be stable. No, it will be unstable. So this should be stable. I think this should be stable and this should be stable. Can you double check it? I'm not sure. Yeah? So anyway, so this is derivative. And you just need to check for on what branch. So on one branch it should be positive, on the other negative. You just find out where it's positive, where it's negative. So what I feel is when x is large and positive, so it will be positive, therefore it will be unstable. When x is increasing, it's unstable. So it's, I decided, but double check it. Good? So we can do a couple of these kind of problems on